pleasure to introduce today's speaker, Professor Yuxin Chen from the Princeton University. Even though he's an assistant professor, he has done many amazing work. He's well known in the community. This year, he won the President Young Investigator Award from the Air Force Office of Science and Research. So he gave an excellent seminar talk last year, I believe.
Not this year, it's last semester.
And we were so impressed, so we invited him to come back here to tell more about what he has been doing in the research. So without further ado, maybe let's welcome Professor Chen to give his first lecture.
Thanks a lot, Xiaoming, for inviting me. And Xiaoming asked me to give 5 lectures. I don't even have 5 slides, so it's really a hard time for me to decide what to talk about. So I'll have to talk about something that's already a little outdated at this point. But I promise you that I won't be talking about things like more than 4 years old. Okay, so so my talk today is the first lecture. This is joint work with Emmanuel Candes from Stanford. Okay, so the agenda of my 5 talks, I plan to do the following things. In the first 2 talks, I'm going to talk about some kind of low-rank matrix factorization problem using non-convex optimization. Which are sort of like a continuous kind of optimization. The third one, it has a little bit of the discrete nature, so it's more about a discrete optimization problem under certain statistical models. The fourth one, it's about spectral method, which typically is used to initialize a non-convex optimization algorithm, which I'll explain in detail in a few minutes. But in this talk, I'll focus on something that's a little surprising, which is about how to use eigen decomposition-based methods when applied to asymmetric matrices, which has some kind of unexpected things happening there. And the fifth one, actually, it's about inference and uncertainty quantification for noisy matrix completion. Some of you might have already heard about it when I gave the talk a few months ago. I'll try to say a little bit more about that. Okay. The main thing is the blending of optimization or computation with statistics. Traditionally, these fields sort of evolve in a kind of independent way. In the statistics community, people focus much less on the computational side, and in the optimization community, people mostly focus on things without very, very concrete statistical model. It's generic optimization thing. What I try to say is that sometimes if you are able to combine these 2 subjects, they are something that you can say, and maybe you can get much better performance guarantees for each of them. Okay, this is a main theme underlying all of the talks that I'm going to present. Okay, so I probably don't need to motivate too much about why we care about non-convex optimization. If you are a statistician, you probably have to deal with maximal likelihood estimation every single day. Many of them, the log likelihood function is highly non-concave. You might have some constraints on the decision variable. Oftentimes they are kind of non-convex. So in general, if either of them is true, and this gives you a highly non-convex optimization problem to solve, just give you a list of concrete data science applications, from low-rank matrix completion to robust PCA, clustering, dictionary learning, and to the more recent deep neural net. All of them, you have to deal with some kind of highly non-convex optimization problems. And the difficulty of non-convex optimization is very clear. In general, when you have a non-convex landscape, it means that you might have a lot of bad local minima. And if this is true, and it makes it very difficult to find the global solution, at least in general. Okay, and so, but if your goal really is to solve maximal likelihood estimation, unless you can really find the MLE, maybe it's hard for you to say the performance of a local minima. And for example, about 2 decades ago, people already know that if you are looking at neural net, even if you have 1-layer neural net, there might be an exponential number of local solutions there. And if that is true, and then in general, we don't really know how to solve it in a feasible way. Okay, some of the very, very special example, probably everyone here already very familiar with this kind of things. So it's a famous mass cut problem. So basically you have a graph. You want to partition this graph in a way such that it maximizes the total number of edges crossing the partition. So this is a classical problem. And mathematically, this can always be formulated as the following problem with some kind of quadratic objective function subject to some constraint. Basically, each xi represents the membership of each of the nodes. And you want to make sure this is either 1 or -1, so you can encode it as a quadratic constraint. This kind of problem is known to be NP hard in general. Okay, so and it's really a $1 million question. If you can solve this, you are able to solve a lot of notoriously hard combinatorial problems. So if you really can solve it, you are going to win a huge prize for this. But most of the people conjecture that this is going to be a problem that, in general, are not solvable in polynomial time. Okay. Engineers and applied scientists probably are never really intimidated by this kind of NP hardness because they need to solve problems. Even though you tell them that this is hard in general, they might still try to find a way to make some progress. And one of the very powerful paradigm that people have been using at least in the last 10, 20 years is the so-called convex relaxation, which has found a lot of applications in statistics, data science, machine learning, a lot of that. There are two representative paradigms there. One thing is about, okay, if I have a non-convex objective function, let's try to find a convex surrogate to approximate this non-convex objective function, and then you solve the convex function problem instead. For example, if you matrix completion compress something, these are all standard problems that taking this form. Another way is to say, okay, maybe the problem is highly non-convex in the original domain. Maybe we can try to lift the problem into a much higher dimensional space. And if you have some auxiliary variables, maybe you are able to convexify the problem. And then you solve the convex program in that domain. Okay. Just to give you one example, the first example is about convex surrogate. For example, if you want to find some low rank matrix, one thing that you can do, because I have to usually try to minimize the rank function, which is highly non-convex. So maybe what we can do is to find the convex surrogate to approximate the rank function. Usually people use a nuclear norm or some kind of weighted nuclear norm to do that. This actually is a very successful paradigm that has already found a lot of applications in practice. For example, Netflix is really using this kind of paradigm every single day. But there is some issue here, actually. So if you look at the nuclear norm minimization problem, okay, if you look at problems like this, even though this is convex means that you can solve it in polynomial time. But you know that you are looking for a very, very low rank matrix. And low rank matrix usually can be represented in a very economic way. But if you want to just solve this problem, maybe you are inherently operating in the full matrix space, which maybe think about it as an m by m matrix, even though what you are looking for is something that's much smaller dimensional. And this might be a problem if you are solving some large-scale data science applications, because maybe even when you really have a lot of data, a lot of samples. When you are dealing with the huge dimensional applications, maybe you won't even be able to read the data. If you won't be able to store or read the entire matrix. And if this is the case, maybe this actually, even though this is polynomial time algorithm, it's in general still a quite expensive algorithm if you want to deal with large-scale data science applications. Okay. Another thing is about max cut. So what people are trying to do for this, in order to solve this problem, is to do some semi-definite relaxation. So what is a very famous Goldman-Williamson paradigm for solving this is to lift the problem into an n by n dimensional space. So I'm going to introduce a large dimensional matrix capital X to represent little x times little x transpose. And if I do this, by basically convert the original problem into a problem represented by this large dimensional matrix variable, except that I have a rank constraint there. Okay. So now convex relaxation, if you want to do convex relaxation, you basically drop the rank constraint, and this is the paradigm that you have. Again, this is a polynomial time algorithm that you can find some solver to solve. But if you want to really lift the problem into much higher dimensions, oftentimes it means that you have a huge explosion in the dimensionality. Okay, so originally your problem is n-dimensional. Now you have to deal with the n by n dimensional structure. So unless you find some very specialized solver to solve this, if you just feed it to some generic off-the-shelf convex optimization solvers, you won't be able to solve this for large dimensional problems. Okay, so these are the problems for convex relaxation. For both of these problems, matrix completion and max cut, it seems that even though we can convexify the problem, it seems that we are still dealing with a very high dimensional convex program, which might be expensive if you really have to deal with huge dimensionality. So now this observation sort of like motivates a lot of activities happening in the last 4 to 5 years about how to improve the performance of the optimization algorithm. And the idea is very, very simple. Since this kind of lifting idea significantly increases the dimensionality, why don't we just come back to the original non-convex problem and try to solve it directly? And maybe under certain kind of statistical models, you are able to solve the non-convex problem directly, and maybe you can find a global solution. Maybe you can still enjoy the best possible statistical guarantees you have. Okay, so this was the original motivation for this part. So of course, non-convex problems are in general very, very difficult, so I won't be able to say too much about a generic theory about this kind of things. But what I like to do is to focus on maybe one problem. Actually, even though I focus on one problem, actually it has connection to a lot of low-rank matrix factorization problem that I can mention, and also the tensor kind of tensor recovery kind of problems. I focus on this concrete thing to try to illustrate some interesting phenomenon happening there, and then tell you that maybe if you really only want to solve 1 or 2 fundamental problems, maybe you should try to be more careful rather than just looking at resorting to generic optimization. Try to be more careful by exploiting the statistical model underlying the data, and then maybe you can do much better. Okay, so this is going to be the paradigm today. I'm going to focus on this particular problem and show that we can actually use non-convex optimization to solve the problem in the best possible way. Okay, so this is the problem. Many of you might already know this problem. So it's about solving quadratic system of equations. Suppose that I have an unknown object x, which is n-dimensional. Think of n as maybe 1 million dimensional. In a linear regression case, maybe we have some linear measurements about this unknown object, and I want to recover them. Now imagine that even when I'm taking the linear measurements, I completely lose all the sign or phase information, which basically means that now what I'm observing is some kind of quadratic program about the unknown object. So it looks like this. X is n-dimensional, and I have m equations. M is sort of like a sample size or whatever. Now my goal is I'm given this nonlinear system of equations. My goal is to find a solution that's compatible with this nonlinear system of equations. So why do I care about this problem? So perhaps the best motivation comes from physics. Okay, so in optical imaging, okay, if you know optics, you know that optical imaging, you have to operate in the super high frequency domain. And the optical sensors or hardwares are usually unable to record the phases of a light. So what you can only do is perhaps only to record some kind of intensities of a light. Intensity, mathematically, you can think about it as some kind of quadratic functions about the unknown objects. So this problem, which is already a century old, and which is called phase retrieval, is basically about how to recover a ground truth signal or object if you are given intensity-only measurements. Okay, basically you are only given some kind of quadratic measurements. Okay. Okay, so this is about physical sciences, and then moving away from physical science, it turns out that this quadratic problem finds a lot of applications in machine learning. Okay, so this is one example about some kind of latent variable machine learning models. So it's a problem called mixture of linear regression. Think about the simplest possible case. Imagine that, okay, I have, x is my feature, beta is my, unknown coefficients. Imagine that my data not only come from one linear model, but come from a mixture of two linear models. One represented by coefficients beta, the other one comes from coefficients minus beta. This is a toy example, but this can be significantly generalized. Okay, so if you have this problem, but every time you draw a data, you don't have the labels, so you don't really know which components your data comes from. Okay, so for example, with probability half, your data looks like the linear function between linear product of x and beta. Or it is also possible that you have x in the product between x and minus beta. Okay, so basically this is there's one bit of uncertainty there. And if you look at this, basically what this is saying is that you don't know the label, and mathematically, basically for this model, it means that you don't really know the sign of this linear measurement. So equivalently, this is about saying that, okay, what you only observe is some magnitudes about this linear model. Now the goal is still to recover the coefficients for each of the components, which basically boils down to how to solve this quadratic system of equations. Okay. So this is the problem called mixture of linear regression, which received a lot of interest in the machine learning society in the last few years. Moving beyond this, more recently, there's a group of people from USC, Stanford, they try to say, okay, let's try to make some progress towards solving the neural net. And they start by looking at some one-layer neural nets with some very, very special kind of activation function that looks like a quadratic function. Okay. Of course, this has nothing to do with practice, but what they are claiming is that if you are able to understand this simplistic model, maybe it can shed some light towards understanding a more general kind of deep neural net. So if your activation function really takes a quadratic form, and what you can see is that the output of the neural net can be viewed as some quadratic functions about the unknown weight of the neural net, and as a result, if you know how to solve a quadratic system of equations, you will know how to learn this neural net in a reasonable way. All right. Finally, I also want to mention that solving this quadratic system of equations has a lot to do with the so-called low-rank factorization problem. So basically, if you look at this quadratic constraint you have, if we introduce an auxiliary matrix capital X to represent little x times little x transpose, similar to what we do for the mascot problem, you can basically convert this quadratic constraint in little x to linear constraint in capital X. So basically, this means that the problem is essentially about solving, finding a rank 1 matrix given a set of linear constraints, even though this kind of linear measurement is a bit structured. And if you want to do convex relaxation, as I mentioned for the max cut, basically what you are doing is just to remove this rank constraint. And if you solve this problem, and this is already the convex program you have, and this convex program works very, very well. Statistically, if you have some random quadratic system of equations, there are a lot of statistical guarantees that people have been able to find for this problem. And in many different aspects, this problem is optimal statistically. Now the issue, however, is that, as I mentioned, if you lift the problem into higher dimensions, you are significantly increasing the dimensionality of this optimization problem. And because of that, we suffer from a huge increase in dimensions and hence in computational burden. So if you just feed it to some special, generic semi-definite relaxation solvers, you probably won't be able to solve the problem for more than 200 by 200 dimensions, which is a terrible thing for us in practice. Okay, so our goal is to find a way to solve this in a much better way. Okay, so let me give you a little bit of the prior art before this work. Actually, this work is already a few years old. So let me try to give you some prior work about some popular paradigm in terms of both the sample complexity and computational cost. And then this will motivate better about why we want to do this non-convex optimization. Okay, so I'm going to plot two things. There's one thing about computational cost, and there's another thing about sample complexity. For this problem, it's basically about the number of equations you have. If you have more equations, usually it means that, at least statistically, it's easier to solve the problem. Okay. So there are two fundamental limits there. Okay, sample complexity-wise, since my goal is to recover an n-dimensional object, so even if you know the phases, you need n measurements, n equations to do that. So it seems that we have a lower bound in terms of the sample complexity. We need n equations in order to enable faithful recovery. Computationally, unless you want to throw away data, okay, well, of course you can, but suppose that you want to use all the data, and then even reading all the data once take time m times n. M is the number of equations, n is the dimension of the problem. So this seems to be a lower bound there. Okay. So basically, if you want to have some linear time algorithm, you have to have the complexity m times n. Okay. These seems to be two fundamental lower limits there. Now this is the performance of the convex relaxation paradigm. Convex relaxation is very, very good in terms of the sample complexity. Okay, so it's almost like the best possible things that you can ever hope for. But computationally, it seems to be quite expensive. So on this curve, usually people need like something that's much larger than m times n squared in order to solve the semi-definite relaxation problem in general. Practically, it works even worse. Actually, it works even much worse than this. So a few years ago, by Emmanuel Candes' group, they come up with algorithm which now is commonly referred to as Wertinger flow. Basically, it's a kind of two-stage method based on gradient descent to solve this. And the original theoretical guarantees provided there looks like this. So I suffer a little bit in terms of the sample complexity. It's not optimal, but it's only a logarithmic factor away from optimal. But the computational cost, at least the theory provided in that paper, is much, much larger than a linear time algorithm. So it's n times larger than that. So if your n is really like a 1 million dimensional problem, and you can imagine that this is going to be slow. Okay, and there is another algorithm called alternating minimization with a system of some kind of sample splitting. Basically, what it means is that you are going to run alternating minimization, but every iteration you use new samples to do it. They run it, and then it turns out that, of course, you are not going to be optimal in terms of the sample complexity because you are using new samples every single iterations. but computationally seems to be much better than the other one. Okay, so this is the kind of state of the art before this work. And what I'm trying to present is to say that actually if you have a nice random quadratic system of equations, maybe you can simultaneously achieve the best of both worlds. So sample complexity-wise, you should be able to achieve the best possible thing, comparable to convex relaxation, but computationally you should be much, much better than that, as long as you are doing this in a more careful way. Okay. Okay. So this is a quick summary of our results. So we are able to, in addition to that, we're not only achieving minimal samples complexity, we should be also able to achieve minimax statistical accuracy. I'm going to discuss this in detail. Okay, so this is the basic thing that I'm going to present today. So how to do it? So usually what we start by thinking about some statistically attractive program like maximal likelihood estimation. Okay, so imagine that you assume that your data are generated independently. You might end up having this maximal likelihood estimation problem. Okay, so what does it look like? So imagine that if you assume each of the data is corrupted by some Gaussian noise, and then you will have some kind of least square problem to solve. If you have some Poisson data, which is probably more common in the optical imaging applications, because the optical noises typically takes the form of Poisson noise. And if you do that, you might have a different objective function to look at. For either of them, in general, they look like highly non-convex, actually for this case, non-concave landscape, which means that in general, you won't be able to solve it in a satisfactory way. Okay, so this is the issue. We try to solve maximal likelihood estimation problem, but there are many of the local stationary points there that we need to be very careful about. So Wertinger flow, the algorithm that I just mentioned by Emmanuel Candes group, proceeds in the following way. So first of all, I try to find a good initialization via some kind of PCA kind of problems. It's more like a spectral method kind of thing. I'm going to explain each of them in detail. And the second step, it looks like a gradient descent. The reason that they call it Wertinger flow is that they want to solve a complex value problems. In complex value case, you don't really have gradient, but there is something called Wertinger derivative there. So you can operate in using this kind of variance of the gradient. But if you only care about real problem, this is the second stage is basically just gradient descent. Okay, and this very, very simple paradigm empirically works much faster than convex relaxation, and it has already achieved quite a bit of success in terms of the theoretical guarantees. Okay, so why does it work? Okay, let me start by explaining each of the stages and then also point out what are the issues there and how we can, further improve the theoretical performance. So I'm going to start with initialization. Initialization, recall that my problem is yk equal to ak transpose x squared. Let's focus on the real case, and I have m equations. X is n-dimensional. This is my problem. Let's look at the random quadratic system of equations by assuming that each of the AK it's generated in an LID Gaussian fashion. Okay, it doesn't have to be Gaussian, but Gaussian is a good point to think about this problem. So if I have this, now if I want to find a rough guess about the ground truth X, we can do the following thing. So let me form a data matrix capital that looks like this. Why do I want to use something like this? Because if I have that model, And if I take the expectation of y, okay, I do the, so let me do some very, very simple calculation for you. If I do that calculation, you see that it looks roughly like identity matrix plus some rank 1 components. And this rank 1 components reveal the information about the unknown object. Okay. Okay, at least for this model. So this is a rationale. Since if I have many, many samples, if I average them out, it seems that I'll get to this point. So if you really believe that your data matrix Y converges to its expectation, and then maybe you have, you have some belief that we can really find, at least approximately find, the ground truth information. So this is a rationale for this spectral initialization. Very, very simple. It allows you not to solve the problem in the best possible way, but hopefully it gives you a lot of information about the ground truth. Okay, let's try to see a little bit of the numerical performance to see whether this algorithm really works in practice or not. Okay, so this is a Stanford quad image. This is a ground truth X. It's like 500,000 pixel. Okay. Now I have a lot of equations about this this image, which I take it roughly like 12 times the dimensionality if I choose the sample size to be that large. And let me run spectral initialization, and then I plot it for you. Okay. So it seems that from this plot, it's very difficult to find any information from there. Right. This seems to be something that looks completely like noise. It doesn't really seem to reveal much information, even though the theory seems to suggest that if I have many, many data, I should be able to do something reasonable. So why is this? Why does it happen? Why is it not really matching the theory that well? Okay, so the issue basically is saying that, as I mentioned, if you really find the expectation of this y, it's working very well. But the thing is that this data actually does not really converge to the to its expectation in a reasonable way, unless you really have a huge number of samples. Why? Because this matrix, it's an average of a lot of random components. Each of the components is heavy tail. So yk is a quadratic function in ak. So each of the components is like like a degree 4 polynomial in ak, which in general it's a highly heavy tail kind of distribution. So if you really have a heavy tail distribution, it means that it does not really converge well unless you have many, many samples. And in fact, numerically, it's very, very easy to find some direction of y that gives you higher energy compared to the ground truth direction, which means that if you just do principal component analysis, it's not going to give you the best possible thing. So to summarize, the problem is the following. If you have large so if you haven't have too many data, some of the data might have too high of a leverage on the principal component directions, and which means that if you average them, you are not able to, you don't have sufficient data to average out the undesired data, which sort of like bias principal component direction. So what is perhaps, this is something very, very simple. What we can do is basically to try to regularize this a little bit. I know that if yk is too large, this is going to be bad because this has too much of the influence on the principal component. What I can do maybe just to throw away some of the large data. So every time I check the data, if each sum of the data is much, much larger than the average, and then if I throw it away, otherwise I keep it. So this is sort of like a truncated version of principal component analysis. And just by doing this, it turns out that you can significantly improve the performance of that. And of course, you probably don't just something better. You probably don't just want to throw the data away. Maybe what you can also do is to just reshape the data, and you. This actually has been improved by Andrea Montanari's group. They basically Okay, if you not throw away the data but give them a reshaping function that looks like this guy, you are able to achieve the information theoretic limits, even including the pre-constant. Okay. Okay, so this is a basic paradigm. If I want to have a rough guess, I probably can just run spectral initialization, and it seems to be working very well. By just doing this kind of truncation operation, you can see that now, if you add your initial guess, seems to reveal a lot of information about this sample quad image, meaning that we're getting a much better initial guess. Okay, so after this first stage, if you do it carefully, the algorithm gives you a rough guess, which is a very nice starting point for you if you want to run non-convex optimization, because it's sort of like make sure that you're in a nice region, and if you are able to start with a nice region, maybe the landscape of the non-convex optimization problem is not that bad. Okay, so this is the first stage. The second stage looks like the following. Okay, so in the original Wertinger flow paper, what they are basically doing is some kind of gradient descent. Okay, so you do gradient descent with respect to kind of whatever log likelihood function you have. So in optimization theory, if you want gradient descent to converge fast, usually we need two conditions. So hopefully, at least locally, we hope that maybe it has some kind of, at least in a restricted sense. Also, we hope that it is a smooth parameter space. If that is the case, maybe we can perform in a very good way. Unfortunately, if you look at this particular problem, there are two issues there. First of all, the objective function, actually this should be L rather than, should be minus L. The objective function is not strictly convex unless the number of equations you have much larger than the number of parameters. The second issue, which actually is a more important issue, is actually this function actually has a huge smoothness parameter. So smoothness parameter basically means the Lipschitz constant of the gradient of this of the problem. So even locally, you don't have nice strong convexity, and your smoothness parameter suffers. So this sort of means that if you just use standard gradient descent theory, it's not going to give you a very attractive performance guarantees. Okay. So why does it happen? It basically means that if you don't have too many data, if you just look at your gradient components, your gradient component looks like this. So Z is your current iterate. X is the unknown object that you want to recover. So if you look at the gradient components, most of them are actually quite good. Actually, most of them, which I plot in blue, sort of like point towards the right direction in some sense. There are always some overly large components which are plotted in red, which are sort of like moving too fast, and you don't have enough data to average out this undesired components. So in a nutshell, this says that the problem of this of gradient descent for solving this problem is that unless you have too many data, the descent direction has a huge variability there. And if you have a large variability there, you are not sure that your gradient component, gradient direction, is pointing towards the right direction. So this is sort of like a variance issue. There is too much variance there you need to take care of. So what we propose, specific to the model, is that, okay, let's try to, since there is too high of a variance there, so let's try to reduce the variance, making sure that gradient descent can proceed in a much more stable way. The algorithm looks like this, but you don't need to worry too much about what this equation says. Informally, this is saying that, okay, let's try to find a way to detect which gradient component is large. If I find some of them are overly large compared to most of the other components, just throw them away. And I will form the gradient direction based on the rest of the gradient direction. So this is what I mean here. So I'm trying to not use all the data, but every iteration I try to detect outliers there. And I only average the set of gradient components with regular magnitudes. And just by doing this, it seems that we can significantly improve the performance of this. Okay. So of course, since I'm throwing away some of the data, I'm actually introducing a little bit of the bias. But the good thing is that just by this very simple thing, I'm significantly reducing the variance. And if we can do that, and when bias and variance effect put together, we're actually getting something that's much, much better. So just a little bit of the visual illustration. Without this kind of truncation steps, because of the presence of this red large outlier components, you are not able to move very fast. You need to be very, very careful, which means that you might have to choose a step size that's very, very small. But after you get rid of these red components, now you are able to choose a step size that's much, much larger. It means that you are proceeding much more aggressively, but without jumping out of the right region. And to summarize, this is the algorithm we have. We start by a careful version of spectral initialization. After that, I do some careful version of gradient descent. And we are adaptively discarding some of the high leverage data, and in order to make sure the algorithm performs well. Okay. So this is a theorem that we have. If you have this particular model, and if you don't have any kind of noise, so basically yk is exactly given by this quadratic constraint, just by running this algorithm, this is what we can say. So suppose that the number of equations you have exceeds the order of the number of parameters you have, roughly exceeds 3 or 4 times n, then you get some kind of linear convergence. So this distance function, think of it as some L2 distance. I'm introducing it because there is one bit of global ambiguity that we won't be able to solve. But up to that, basically you can treat it as a L2 metric. So this L2 metric converges geometrically fast to 0. Here, rho is really a constant. It is a constant that's dimensional free. So think about this as 0.1, regardless of the dimension. So to summarize, what this theory is saying is the following. First of all, after initialization, I'm able to be reasonably close to the ground truth. And within this nice region, even though this is non-convex, this is some kind of landscape that we can take care of. After that, we have linear convergence, and the total number of iterations needed to achieve epsilon accuracy is really log 1 over epsilon. Okay, so this is about the iteration complexity. You might wonder what is if you want to understand the total computational cost, there's one more step. You want to understand what's the cost for each of the iterations. This is something that you can get. Okay, so if you want to run in spectral method, basically you are computing the leading eigenvector about this matrix, which basically what you can do is to run power method. If you run power method, this matrix can be written in this form, some A matrix times some diagonal components times another A matrix. So each of the power iterations, you run your data twice. Okay. So, and for each of the gradient iterations, it can also be written in this very, very simple form. So basically, you also run your read the data twice, and that's it. That is the cost for each of the iterations. So for either the initialization part and the gradient descent part, each iteration only takes you, takes you 2 applications of the data matrix. Now, if you know that it converges within 100 iterations, basically sort of means that you need to read the data 200 times, regardless of the dimension, and then you are done. Okay, so in total, oftentimes, maybe just several tens of applications, it gives you a very, very good accuracy for solving this problem. So numerically, let me try to show that this is not just something of theoretical interest. This is something that works very well in practice. In order to do that, I'm going to compare the performance of my algorithm with some baseline. And I'm going to pick the baseline in such a way that, in a way that is much, much easier than solving this quadratic problem. So basically, I picked the baseline to be just solving a linear system. So I tell you all the unknown phases. So this is my original problem, but I have a lot of unknown phase for sign information. I give away all the sign information. I let you solve the linear system using one of the most popular algorithms like conjugate gradient. Now you compare the performance of these two things. I'm rescaling the axis a little bit, but basically what this plot is saying is that solving this quadratic system using our algorithm takes time roughly like 4 times that of solving a least square problem of the same size. In fact, I think there is some follow-up work by Yingbin Liang. They say if you do a truncation step in a slightly different way, and they are even able to make sure that the computational cost of this algorithm is almost the same as just running the conjugate gradient for solving the same problem. Okay, so this seems to be something that's very, very nice. If you are able to solve a least square problem using conjugate gradient, maybe you can actually use our algorithm to solve quadratic problem, even though this is much harder problem. Empirically, as I mentioned, after the spectral initialization step, we get the image like this. Then you run maybe 50 iterations. You get almost noiseless picture for this. Okay. How much time do I have? 10 minutes. Okay, so maybe let me skip this part, but let me talk a little bit about the stability side. Okay, so what I have mentioned so far, it's about how to solve the problem if your data is clean, so there's no noise. Of course, if you're a statistician, you probably care about the noisy case. So the data typically are corrupted by some kind of noise. It's in particular in the optical imaging applications, your data are always noisy, so you have to deal with that. Okay, let's take a look at the noisy data scenario. K now is my noise. Okay, let's assume the noise are independently generated. Then I define some kind of signal to noise ratio in this way. Okay, so I'm going to forget about what this is, but this is SNR definition specific to this particular model. And again, I'm going to assume that I have ID Gaussian design so that I can say something concrete. Now, so what prior work says is that if you have many of the data, actually this needs a condition saying that the sample size is much, much larger than the number of parameters you want to recover, then Wertinger flow converges to the maximum likelihood estimation. What we are able to say is that using the algorithm I just mentioned without any modification, you just run the same algorithm over the noisy data, and you won't be able to achieve perfect recovery because you have noise, but you are able to make sure that you have a performance and to accuracy that looks roughly like 1 over square root of the SNR. And numerically, I'm plotting the performance as a function of SNR, and you see that when I change the sample size a bit, the slope doesn't change. Basically, it sort of means that the relative mean square error of my solution roughly scales inversely with the signal to noise ratio, which is basically what our theory predicts. So it seems to match what the theory says. Now the question what you naturally want to ask is this the best thing that we can do? It turns out that it's almost yes. So let's try to do a little bit more of the empirical experiment to show that actually this is the best possible thing that we can do. So I'm going to compare it with MLE with some side information. So I ask you to solve the MLE, except that I tell you all the unknown sign information. So I reveal all the unknown information to you, ask you to solve the MLE. And if you do that, now you compare the performance numerically. This is the performance of our algorithm. This green line is a performance of an MLE with some Gini revealing extra information to you. So this looks like, in an engineering term, looks like only a small number of, this is basically like 1 dB loss compared to something that you know you won't be able to improve upon. Okay, so this is empirical thing. Theoretically, we can also justify that actually this is the best thing that you can do. So if you really have Poisson noise with this SNR definition, we can actually show that there is a minimax lower bound there. So there's a minimax, there's a statistical bound says that within the very reasonable range of the signal, the best possible thing that you can do from a minimax sense is 1 over square root of SNR. If the sample size is really close to the information theoretic limit. Okay, so this is a lower bound, which also matches our achievability bound, somehow implying that non-convex optimization is not only fast, it allows you to achieve the best possible statistical guarantee in terms of the statistical accuracy. I'm going to skip this part. I just want to mention one more thing. I have mentioned that it's one paradigm. In order to simplify analysis, people say, okay, let's run optimization algorithm by each iteration. Let's use new data so as to simplify analysis. Practically, at least for phase retrieval, nobody's going to split the data because we have very, very limited data there. So usually in physics, you won't be able to collect too many data. And if this is, if you're operating in a sample starved regime, you won't be able to split the samples. And so that algorithm is not going to be very useful for this particular problem. But what we are trying to say theory-wise is that you don't really need to, you can split the samples, but you don't have to. Even though you don't split the samples, you are going to have the best possible theoretical background. After this work, there are lots of people that have follow-up. So there are many, it turns out that there are many other non-convex algorithms which are all fast, all achieving the very nice statistical guarantees. This might include alternating minimization without any kind of resampling, include some kind of composite optimization, basically treating the objective function as some composition of the smooth function and some convex function. You can use a message passing to do this. You can do block coordinated descent, many of them. If you analyze them in a careful way, all of them seems to achieve the best possible performance. There is some difference in terms of the constant, but up to the order, all of these are optimal. Okay. You can also do stochastic version. You also have different kinds of initialization that can improve the theory. There's some other people, some other group try to understand why so many algorithms work simultaneously for this problem. So they try to start by looking at some geometric analysis by saying that actually if you have data, the landscape of the problem is actually so nice that maybe you can expect a generic optimization theory. But again, this requires you to have many data. But if you really want to operate in the regime where the sample complexity approaches the information theoretic limit, this is not going to be applicable. Tomorrow I'm going to mention two different things of interest to this particular problem. First of all, I want to say if you want to analyze gradient descent, actually the way that I just mentioned is highly suboptimal. This which is based on generic optimization theory, but it doesn't really help you understand the right performance of this, this particular problem. Also, I like to say that maybe even initialization is not really needed. Maybe you can just do random initialization. It seems to be also working very well. Okay, this is something that I'm going to talk about tomorrow. The central message here is that if you really have a statistical problem to solve, if you can exploit the data model in a more careful way, maybe the very simple non-convex paradigm are surprisingly effective for solving problems of this kind. And there's a very important, I think I want to highlight the importance of blending statistics and optimization, which can give us much better understanding about simple algorithms. And finally, I like to say that non-convex optimization sometimes seems to be much more effective compared to convex relaxation. And this is summarized in this paper. Thank you very much.
Do we have anyone who wants to ask a question now? If not, Professor, this is not a regular seminar talk. Professor Chen will be here until the end of next week. So you can always find him and talk to him if you have any questions. So let's thank him again.
Yeah. Thank you.